So now let us look at a few trigonometric limits. Now these are limits which are standard, of course, and it is recommended that you remember all these standard results, because it would become very difficult for you to solve this manually in the examination using the Maclaurin series or the Taylor series step by step. So it is better that you remember this, and based on this you would be able to solve any other question where there are difficult functions given. So for example, the first one is limit extending to 0 sin x by x, which is 1, extending to 0 tan x by x, which is 1 again, and 1 minus cos x upon x square, this is 1 by 2x. Now it is not necessary that this value, which is x, it needs to be x only, or it needs to be a single coefficient value x. It can be, let's say, 2x, it can be x square as well. So now the function would change a little bit. Let's say if I have, instead of x, I have x square. So in each and every place, I will simply replace x by x square. So this would become limit x tending to 0. Let's say if I have sine of x square. So this would become, below also I would have to put x square, then this would become 1. So it is basically sine of something. This is not x. This is sine of something upon something would give us 1. So keep this thing in mind. Now in all these trigonometric limits, it is important for you to note that x is tending to 0. Let's say instead of 0, had x been tending to any other quantity, then this standard limit wouldn't have worked for such cases. So it is necessary for you to note that x should be tending to 0, then and only then all these trigonometric limits work. Now, if I was to give you a little bit of proof as to how this basically standard trigonometric limit is coming out to be. So later on in our later lectures as well, we will study about Taylor series, or also known as the Maclaurin series, where there is a formula, differentiation, and all those things related. You will learn about that in those slides only. So I'll just give you a brief overview. Generally, whatever type of function is given, it can be opened up or it can be expanded using the Taylor or Maclaurin series. So for example, sin x, how does it open up as? It opens up as x minus x cube by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial, and this goes on up till infinity. So this is how sin x can be opened up using Taylor series. So now let's say if I was to replace this entire expansion in my simple function here, limit extending to 0 sin x by x. So instead of sin x, I can write this entire expansion here. In this entire expansion, what you can see is I can take x to be common. So it would become 1 minus x square by 3 factorial plus x to the power 4 by 5 factorial minus x to the power 6 by 7 factorial, and this would go on up till infinity, right? And below we have x. Now in this entire expansion which is inside the brackets, you know that in each and every term there is going to be an x value which is going to be of some power or other, right? So here what you can see is that x and x would get cancelled out amongst each other. Now in the value which has been left inside, what if I put x as 0 simply? So this would become 0, this would also become 0, this term would also become 0, and like this each and every term up till infinity would become 0. Only thing that we would be left with is 1 in the start, so this becomes our answer. So this is basically the proof of how such trigonometric limits are found out. Similarly for tan x also, you can use the expansion of tan x using the Taylor and Maclaurin series. Write down its expansion, take x common, and from there you'll get that answer. 1 minus cos x upon x square. For cos x also there is an expansion. You can use that, find out your answer. So keep these things in mind. Let's look at a few more. Let's say instead of x, as I mentioned, instead of x, if you have sine of kx, then it is basically limit x tending to 0 sine of something upon something. So here, if you look at this example, how can I write this down as sine of something? What is this something here? Kx. So what I'll do is, below I have an x here. This is limit x tending to 0. So what I'll do in this function is, I'll multiply the numerator with k and the denominator with k as well. So if you look at the denominator now, Now it has also turned into kx. So sine of something upon that same something, this value is 1. So if this is 1, what are we left with? Only k. So that is how we get k as our answer here. So again, for tan x, sin x, it is not necessary for you to remember this. You can simply proof it during your examination as well in this manner. So for sine inverse x, also the same kind of standard limit works, where we have limit extending to 0, sine inverse x by x becomes 1, limit extending to 0, tan inverse x by x becomes 1. Now if you look at this example, limit extending to 0, sine x by tan x, this is 1. So basically, if I was to show you the proof of this, I'm having sine x by tan x. So I hope you all remember that from here we can see that sin x by x is 1 and tan x by x is 1. And we know whenever we are using limits, this was a property that we studied. Let's say if we have two functions in the division format, so it would become limit extending to 0 sin x upon limit extending to 0 tan x. So I can take them separately as well, right? So if I take this limit to be separately, so this would become limit x tending to 0 sin x whole by limit x tending to 0 tan x. Now I know that sin x by x basically is 1. So I would divide this by x and I would also multiply an x here. Same for tan x. I'll divide this by x and I'll multiply an x here. So from here we know that this value is basically 1. This value is also 1. So we have limit extending to 0 x limit upon limit extending to 0 x. So x and x can get cancelled out simply and we would get 1 again. So this is how generally you are supposed to solve questions related to such trigonometric limits. Of course, it is recommended that you remember such results. Otherwise, solving it using the Taylor-Maclaurin series would become very difficult during the examination. Here, what if, let's say, my x is tending to infinity instead of 0? Now, as I mentioned, you must remember that x is tending to 0 for such limits to exist. Now, what if, let's say, instead of 0, I have x tending to infinity? So, if you look at this limit here, where x is tending to infinity, I have sin x by x. I know that my range of sin x basically belongs from -1 to 1, right? That means if I look at sin x by x, if I put the value of x as infinity, whatever be the value of x, I would get the range as from -1 to 1 in the numerator, right? And in my denominator, if I'll put x as infinity, what would I get? X would simply become infinity here. So now whatever be the value on top, below I know that I have an infinity. So this entire term would simply become 0, right? Because if in denominator, as soon as I start increasing my value of denominator, my entire value of function starts decreasing, right? So similarly, once it reaches infinity, that means my entire term would simply become 0. So that is why limit extending to infinity sin x by x becomes 0. So keep this thing in mind as well. Now again, a few more properties. Let's say if it is reversed, it becomes x by sin x, then that value is always equal to 1. We have 1 minus cos of kx upon x square. Now this one, I hope you all remember, it was cos of something upon something squared. So here what do we have as something? We have kx. So below also what we'll do, since we have just x square, I'll multiply k square, the numerator as well as the denominator. So I know that this value would basically become half. So from here I would have k square by 2 as my answer. So keep this in mind as well. Let's look at this question. What has been given to us? Evaluate x tending to 0, 1 minus cos 2x, 3 plus cos x upon x tan 4x. So what is our first thing that we are going to do? We are going to put 0 in this entire equation. If we put 0, what are we getting? We are getting it to be 0 by 0, which is an indeterminate form. That means at x tending to 0, we cannot have a value for this equation. Now what we'll do, we'll try to solve it in some other way using our limits. So 1 minus cos 2x. I hope you all remember whenever x is tending to 0, we have limit x tending to 0, 1 minus cos x upon x square. It gives us half. So there are a few trigonometric limits that we are going to be using in this question. Let me write those down for you. So the trigonometric limits that we are going to use here are, the first one is 1 minus, sorry, let me write it down completely. Limit x tending to 0, 1 minus cos x upon x square. This value is half. So we can use it in this function. For tan x, we can use another limit that we know, which is tan of something upon something gives us 1. So simply what I'll do in this function is, first, I'll write down 3 plus cos x since I need to leave it as it is. I cannot do anything for it. And also, if I put cos x as 0, I would get this value as 4. It is not going to be 0, right? So I do not need to worry about this particular function. Apart from that, I have 1 minus cos 2x here. So what am I going to do? I'm going to divide this function by 2x whole square and multiply it as well by 2x whole square. So now you can see that 1 minus cos 2x has been formed upon 2x whole square. So this would simply become half. Below, what else we have? X. I'm going to leave it as it is. And then we have tan of 4x. So now to remove this tan of 4x, what I'll do is I'll multiply this with 4x and divide this as with 4x as well. Now since we have limit extending to 0, we know that this term here, this term is nothing but half, and this term here, tan of 4x upon 4x, this is nothing but 1. So from here, what do we get? Limit x tending to 0, 3 plus cos x. And here we have x, 4x. Basically, this 2x square and 4x square would simply cancel out amongst each other. So we would have nothing left here. So we are just left with 3 plus cos x. Now if I look at this function, sorry, there is going to be a half as well, divided by 2 as well here. So now if I look at this function, what if I put x as 0 simply? So I would get 4 by 2. This is nothing but 2. And this is my answer. So this is how you must solve your questions. Once you get a function where, let's say, you are not getting any type of indeterminate format, you can simply replace your value of x as whatever it is tending to and give your answer. So this is how you must solve such questions. Now, a few more limits that you need to remember. We studied about trigonometric limits. Now for exponential as well. What if you have 1 plus x to the power 1 upon x? This basically becomes e. Now the way of solving this is, of course, taking ln both sides. You would have 1 by x come to the sides and then trying to solve it, removing the ln from our y. So again, the proof is basically from the Maclaurin series or from some logarithmic series which you can use here. But it is recommended that you remember all these uh, limits so that it becomes easier for you to solve during the examination. So what if I have limit extending to 0, 1 plus x to the power 1 by x? So this basically transforms into 1 to the power infinity. This is my indeterminate form here. So this becomes e. So one thing that you must remember here is that whenever you have 1 to the power infinity, or let's say anything to the power infinity or 0 or something like that, whenever power comes in our questions, what is the method that we are going to use to solve such questions? We are going to use our logarithmic series or some type of exponential values to solve such questions so that our power can come below and then we can solve our limits. So keep this thing in mind. Similarly, when x is tending to infinity, we have 1 plus 1 by x to the power x. Instead of x, we are putting it as 1 by x. So again, we would get e. Limit x to the power x extending to 0 plus, we would get 1. Extending to infinity, e to the power minus x, this would simply become 0. I hope you are understanding this. E to the power minus x, this basically means 1 by e to the power x. And what if I put x as infinity in this function? So I would basically get 1 by e to the power infinity, which is nothing but 1 by infinity, and this is nothing but 0. So this is how this limit is getting solved. So keep this thing in mind as well. Similarly, let's say if I have only limit e to the power x, that time I have x tending to minus infinity. That time it becomes 0. Now a few logarithmic limits as well. Let's say x is tending to infinity, we have ln x by x, it would become 0. Limit x tending to 0, ln x, this becomes minus infinity. Limit x tending to infinity, ln of x to the power n upon ln x, this would become n simply. Limit x tending to 1, ln x upon x minus 1, this would become 1. So simply few results that you need to remember. Again, instead of let's say exponential, what if we have a to the power x? A to the power x minus 1 upon x, this would become ln a. E to the power x minus 1 upon x, this would become ln e. So we know that its base is also e for ln, so it would basically become 1. Limit x tending to 0, ln of 1 plus x by x, this becomes 1. So this one is the most important one. Remember this. Limit x tending to a, x to the power n minus a to the power n upon x minus a, this would become n into a to the power n minus 1. Keep this limit also as well in mind. This is also an important one. So basically, how are we solving this? X to the power n minus a to the power n. What I'm doing is I'm taking x minus a common from this term. What would I be left with? X to the power n minus 1. And then in my next term, I would have x to the power n minus 2. And this would go on up till infinity, till we have x to the power 0. So basically, if I put x as a in my entire function, I would receive all terms to be 0 or get cancelled out amongst each other. And in the end, I would only be left with this. So that is why I get this as my answer. So these two are important properties. Keep in mind these two properties. Let's look at this question, how this question is solved. Limit x tending to 0, 1 minus cos square 3x. Now I hope you all remember the trigonometric limit that we studied. It was 1 minus cos x. It wasn't 1 minus cos square x. So this cannot be solved using that way. So do not confuse yourselves. It is 1 minus cos x and not 1 minus cos square x. So how are we going to solve this then? It can simply be converted into sine square 3x. 1 minus cos square x is basically sine square x, right? So this would become sine square 3x, and then we can solve it using our trigonometric limit that we studied. So basically what I'll do is I'll first write this entire term properly. 1 minus cos square 3x, it can be written as sine square 3x. We have sine cube of 4x whole divided by cos cube 4x into ln of 2x plus 1, or simply what I'll do is I'll take 2 common. So this would become x plus half. This whole is to the power 5. Or I'll just let it be as it is. I'll let it be 2x plus 1 only. So now I'll try to use my trigonometric and exponential and logarithmic limits to solve this. So what are the limits that I'm going to be using in this question? First of all, my first limit would be, of course, limit x tending to 0, sine x by x, which becomes 1. Second limit that I'm going to be using, it is going to be limit x tending to 0, ln of 1 plus x upon x. This is also equals to 1. So what I'll do here is, first of all, I'll see this sine square 3x. So to remove this, what I'm going to do, I'm going to divide this by 3x whole squared. I'm going to multiply it by 3x whole squared. So this term basically would become 1. This is nothing but 1. Now I'll look for sine cube 4x. I'll divide this by 4x whole cube. I'll multiply as well 4x whole cube. So this term also simply gets removed and becomes 1. Now I'll look for ln. So what I'll do is, since this is whole thing is to the power 5. So what I'll do is, since this whole thing is to the power 5, I'll divide this by 2x and multiply this by 2x. So outside my bracket, I'm going to have 2x whole to the power 5. I hope you are understanding this. Since I have ln 1 plus 2x whole to the power 5. So what I'll do is I'll take 2x below inside the power 5, and then I'll multiply a 2x to whole to the power 5 outside, so it can simply cancel out amongst each other. So this value now inside the power, this also becomes 1. So from here, what am I basically left with? I'm left with 3x square into 4x cube upon cos cube 4x into 2x whole to the power 5. So here x would get cancelled out amongst each other. If I put x as 0, cos cube 0, this is simply 1. So this can be removed. So we are left with our answer as 3 into, sorry, 2 would get cancelled out. We would have 3 upon, sorry, this would become 3 into 3 into 4 into 4 into 4 divided by 2 to the power 5. So from here, these 2 and 4 can get cancelled out. This cancel out this twice. So we get 18 as our answer. So this is how you are supposed to solve questions of limits. Try to identify what type of trigonometric, exponential or logarithmic limits can you use in your question, and then based on that, solve it. Solve your question. Now let's talk about limit of a rational function. So basically, what is a rational function? Whenever we have, let's say, a polynomial by a polynomial, that time we call it to be a rational function. So basically, a rational function is nothing but polynomial upon a polynomial. So let's say if I have x tending to infinity, f of x by gx. So this value would become two constants, am by bn, where I'm saying that f of x is a naught plus a1x plus a2x square and up till am x to the power m. Gx is basically b naught plus b1x till bn x to the power n. Now, when can I say that my solution would be this? When my m is equal to n. Now, there is a condition that this entire equation follows, that m is equal to n. So let me show you the proof. Based on the proof, you would be able to understand this better. So basically, what am I having? I'm having limit extending to infinity, a naught plus a1x plus a2x square plus up till am x to the power m divided by b naught plus b1x plus b2x square up till bn to the power bn x to the power n. Now what I'll do is I'll take x to the power m common from the numerator and x to the power n common from the denominator. So I would be left with limit x tending to infinity, x to the power m, I've taken it as common, so I would have a naught upon x to the power m plus a1 upon x to the power m minus 1, and this would go on up till am. So basically this is the only term am which is going to be free of any x. Below, what am I going to have? I'm going to have x to the power n, b naught upon x to the power n plus b1 upon x to the power n minus 1, and this would go on up till bn. Now if you look at these two equations, of course, since I have x is tending to infinity, that means if I have in my denominator x, that means my entire term would simply become 0, because I would have something by infinity, it would become 0. So here you can see that all these values of x, this would simply transform into 0. All these values are going to be 0 except for this constant. If I start putting the value of x as infinity, all these terms would simply become 0, right? Except for this constant term. So what would I be left with? Basically, limit x tending to infinity, x to the power m into am upon x to the power n bn. Now, based on this, I hope you all can make your assumptions out of this. So basically, what would be the solutions of this? Let's say if m is equals to n, my m is equals to n. So simply x and x would get cancelled out and we would get our answer as am by bn. So this is what the condition basically says. If my m is equal to n, then only I can have am by bn. However, let's say if my n is greater than m. If my n is greater than m, then that means in my denominator, I would have a greater value of x. If n is greater than m, that means x to the power m can simply get cancelled out. And in my denominator, I would have x to the power n minus m. So if I put x as infinity here, then I would have infinity in the denominator. So this would become 0. And if m is greater than n, that means in my numerator I would have an infinity. So this would become infinity, or we can say this does not exist. So you must keep this in mind. Finding out limits of any rational function, what you do is you take the power of x as common, which is the highest. Now this is only when x is tending to infinity, so that you can have infinity in all the denominators of your terms. And then as soon as you put x as infinity in those terms, all those terms would become 0 except for the ones which are constant. So that is how you solve limit of a rational function whenever x is tending to infinity. Let's say x had been tending to 0. If x had been tending to 0, I wouldn't be required to take any x as common. Simply, I could have put x as 0 in the function. I would have gotten a naught by b naught as my answer. So keep this thing in mind. The difference as to how you must solve your questions whenever you have, let's say, x is tending to 0 or you have x tending to infinity. So exactly the same things that we just discussed here have been mentioned here. If m is equal to n, then only I can get this answer. If n is greater than m, I would have degree of numerator as less than denominator, so I would have simply 0 here. If m is greater than n, then degree of numerator is greater, so it would become infinity. If am and bn have opposite signs, that means am into bm is less than 0, then f of x by g of x, this would give us minus infinity. So keep these cases in mind. This would help you solve questions very easily, which are tending to infinity questions. We'll look at one in our example as well. So let's look at this question. So what is our first thing that we are going to do? We can see that limit x is tending to infinity. So we know this is going to be a question of a rational function. So for our rational function, what is the trick that we must use to solve such questions? For any rational function, our x should be tending to infinity. Yes, it is there. And the other thing is that we must check whether it is a polynomial by a polynomial or not. So yes, it is a polynomial by polynomial. Now from this equation, what we can see that our m value is basically 5 and our n value is basically 4. So this is the highest power in the numerator. We will look at the highest power in the denominator. Whenever x is tending to infinity, we just look at the highest powers of the numerator as well as denominator. If we look at both for this function, our m is basically greater than n. That means we are going to have degree of numerator to be greater than numerator, right? So basically, in this question, our degree of numerator is greater than degree of denominator, and x is tending to infinity. And you can see that am by b and bm both are positive values here, so that you can use this case here. Am and bn both are positive values here. So simply this limit, I'm just writing it as f of x, this would become infinity. That means limit cannot be defined. So this is how you must check your questions which are related to rational function. Simply just check the value of m and n, and based on these cases that you've just found out, you can write down your answer. So if you remember these cases, of course, it would become very easy for you to solve. Else now, if you, let's say, do not remember these solution, you would start taking x to the power 5 common in the numerator, x to the power 4 common in the numerator. It would become a quite lengthy question. So if you know such rational function trick, you can directly look at the question, find out your value of m and n, check am and bn, write down the answer. Let's look at this question. Let's say we have limit extending to infinity, root under x square minus x plus 1 minus ax. This value is equals to b. Now in this question, if I put x as infinity, this is going to basically becoming infinity minus infinity, and we know this is also an indeterminate form, because of course you cannot solve infinity minus infinity. You cannot write it down as 0. Infinity is a very big undefined number, and infinity is also a very big undefined number, so you cannot compare these two numbers, right? So infinity minus infinity is never 0. Keep this thing in mind. So how can we solve this question? we can see that this is basically an irrational term. We have root under, we have a constant term outside. So this is an irrational term. So we'll try to rationalize this. How can we rationalize any term? Simply multiply it by its conjugate. So we'll multiply it by its conjugate. We would get limit x tending to infinity. Root under x square minus x plus 1 minus ax upon, what are we going to do? We are going to multiply this numerator by root under x square minus x plus 1 plus ax and divide this as well with this same function. So basically we are trying to rationalize this function by multiplying this and this. So from here, what are we going to get? Limit x tending to infinity. In my numerator, I would basically have x square minus x plus 1, and we would have minus a square x square upon root under x square minus x plus 1 plus ax. So if I take x square common in my numerator, what would I be left with? X square, I would have 1 minus a square minus x plus 1 upon root under x square minus x plus 1 plus ax. So now, can I solve this using the rational function trick? Yes, of course. My x is tending to infinity. I have a polynomial on top. I have a polynomial below as well. So if I look at the highest power in my numerator, it is basically 2. However, in my denominator, my highest power is 1. Here I have x as 1. Here also this x square. Since it is under root, it would become x as 1. So my highest power is 1 in my denominator and 2 in the numerator. So if I need to get a finite value, of course, I need to first of all have both of my powers to be same in my numerator as well as denominator. So what I'll do is, in my numerator, the one which is the highest power, which is greater than 1 in the denominator, I'll put it to 0. So what if 1 minus a square basically becomes 0? If, let's say, 1 minus a square becomes 0, then I wouldn't have this x square term in my numerator. So my highest power in my numerator would become 1, and in my denominator also I have 1, so it would still be 1. So from here, if I put this as 0, I can have values of a as plus minus 1. So these are the values of a that I can choose. Now let me solve for b, what I can get. So there can be two cases. Firstly, when I take a as 1 and a as minus 1. So let me check by a as 1. So I would have limit x tending to infinity minus x plus 1 upon root under x square minus x plus 1 minus ax. So from here, I can see that my highest power in my numerator is 1, in my denominator also it is 1, and x is tending to infinity. So what would my answer become? The highest power's coefficient would become my answer. So from the numerator I have minus 1, and from the denominator basically I have, sorry, a is minus 1, so this would become simply x. So I would have 1 minus 1 from this root under x square minus x plus 1. Of course, my coefficient of x is going to be 1 from this term specifically. If I look at this term, x square minus x plus 1, basically my coefficient of x is going to be 1, right? Because x square would become 1 and its coefficient was 1, so root under 1 would also become 1. So basically coefficient of x is root 1. So keep this thing in mind. So from here I would get 1 minus 1, which becomes infinity. So this case cannot be taken. So I'll have to take a as minus 1. So if I take a as minus 1, I would have limit x tending to infinity minus x plus 1 upon root under x square minus x plus 1 plus x. So from here I would have my answer as minus 1 by 2. So this is what I'm getting my value of b as. Sorry, this was minus 1 and this was plus 1. So this is my value of b. I hope you are understanding this. Now, in my second case, my coefficient of x from this term would simply become 1, and I have a plus 1 as well. I have an x outside added as well. So I'll take that coefficient as well. So I would have minus 1 upon root 1 plus 1. So this would become minus 1 by 2. So what is the ordered pair of a and b that I'm getting? My a is basically 1 and my b is basically minus half. So this is how you must solve questions which are related to rational functions. So keep this thing in mind. Let's look at one more question. Limit n tending to infinity. They've given us a series. Now in this series, they've also given us the rth term. So basically, if you look at this, this is my nth term. So I can write down this as rth term as well. So firstly, I'll try to solve the numerator only. So if I look at my numerator, I have basically summation of 3r minus 2 plus 3r minus 1 minus 3r. So from here 3r would get cancelled out. I basically have summation of 3r minus 3. So from here I can take 3 to be common. So this would go outside. I would have summation r minus 3 times of summation of 1. So if I write down this summation simply in my n format. So what is my sum of n natural numbers? It is basically 3 n into n plus 1 by 2 minus I would have an n here as well. So this is what my numerator is basically transforming into. So now if I try to solve this, this would become n square plus n minus 2n. So this would become n square minus n into 3 by 2. This is what I'm going to have as my numerator. Now if I let me write it down in a more proper way. So I have basically limit n tending to infinity. In my numerator, I have 3 by 2 n square minus n. And in my denominator, I have root under 2n to the power 4 plus 4n plus 3 minus of root under n to the power 4 plus 5n plus 4. So this is what is in my denominator. Now of course this I can see that this is my rational function. It is a polynomial by polynomial. N is tending to infinity. So I can use my rational function trick here. So what I'll do is I'll look at the highest powers of n in my numerator as well as denominator. In my numerator, I have the highest power as 2. In my denominator also, I have the highest power as 2. This n to the power 4, basically once taken root under, would become n square. So I have 2 as my power in both numerator and denominator. So simply what would my answer become? If my powers are same in my numerator and denominator, it would become the coefficient of highest powers of n. So in my numerator, I would have 3 by 2. And in my denominator, I would have basically root 2 minus root 1. This transforms to 3 by 2 root 2 minus 1. This becomes my answer. Now again, you can of course rationalize this further by simply multiplying root 2 plus 1 in the numerator and denominator, so that from the denominator you can remove the root 2 sign. So you can do that. However, always whenever you have n tending to infinity in questions given, try to convert it in such a way so that you can have powers of n in the numerator as well as denominator as same, the highest power is same, and simply their coefficients become your answer.